If I have only one random variable, then we say it's continuous if there is a function lowercase f such that the probability that the random variable takes a value between a and b can be calculated from the integral from a to b f of x dx. The f function is called the probability density function, and it's associated with a continuous random variable. If x is a continuous random variable, then the probability that the random variable will take on a specific value is 0. So we want to extend this idea to the case where I have two random variables. So x and y are now two random variables. In the same way, if they're continuous, then probabilities such as x equal to x and y is equal to y must be 0 for all possible values of x and y. So in order for probabilities not to be 0, we have to consider intervals. So a probability such as x being between a and b and y being between c and d, that is a probability that doesn't need to be 0. We can illustrate an event such as x being between a and b and y being between c and d as a rectangle in a Cartesian coordinate system. So if I put here x and y, this is the interval a to b, and this is the interval c to d. So the event that x is between a and b and c is between c and d is then this rectangle right here. If the experiment ends up in such a way that x and y will map the outcome into a number inside this rectangle, then this event will turn out to be true. So in the single random variable case, a less than equal to x less than equal to b becomes the integral over the real line from a to b f of x dx. However, when we have two random variables, the probability that x lies between a and b and y lies between c and d will then become a double integral, where we need to integrate x from a to b and we need to integrate y from c to d. And the function we will integrate is then a function of two variables, f of x comma y, dy dx. So this is how we would calculate the probability of ending up in a rectangle. However, rectangles are not the only possible shape in R2, so we can do something like this instead. We can define an arbitrary event by just drawing an arbitrary area in the Cartesian coordinate system. This doesn't have to be a rectangle. So let's just call this area A. We can consider an event which we write as x comma y belongs to A. This is the event consisting of all outcome that x and y will map into this area A. The probability of this event, x comma y belonging to A, will then be a double integral, and you can write that either with two integral signs or one integral sign, doesn't make any difference. But the important point is that we need to integrate over this area A. And what we're integrating is f of x comma y dx dy. This is just a generalization from the example we considered up here when A was a perfect rectangle. So this is the idea that we use to define what we mean by two continuous random variables. And at the same time, we define the joint probability density function. So I have two random variables. We say that they are continuous if there exists a joint probability density function, abbreviated joint PDF, f, which is a function from R2, that is the Cartesian coordinate system, into R, gives me a real number, such that the probability of this particular event, that x and y ends up in the area A, that must be precisely equal to the double integral over A of this joint PDF function. And this must be true for all possible areas that you can draw in the Cartesian coordinate system, including but not limited to rectangles. When we had one random variable, then the probability density function was just a function of one variable, f of x. We also defined the CDF, in this case, as the probability that x was less than equal to x. This was the integral from minus infinity to x of f of u du. And by differentiating both sides, we concluded that we could get the PDF by simply differentiating the CDF. In the case of two random variables, x and y, the CDF is defined as x less than equal to x, y less than equal to y. The CDF exists for all random variables and it's defined in the same way no matter what type of random variables we're talking about. So this is the event. If I have a small x here and a small y here, then x less than equal to x, y less than equal to y is this particular event here, going to minus infinity both along the x and along the y-axis. So by definition, this is then the integral where x goes from minus infinity up to the number x, y goes from minus infinity up to the number y, and I need to integrate the joint PDF f. In this case, it's not appropriate to use x and y as my integration variables because we have x and y in the limits. So I replace x and y with u and v, so dv du. This is how you calculate the CDF from the PDF in the case of several random variables. Just need to do a double integral. If you differentiate both sides, first with respect to x and then with respect to y, the partial derivative, first with respect to x and then with respect to y, becomes precisely f of x comma y. And this is how you get the joint PDF if you know the joint CDF.